Hello friends, I am Lalita Palange. Today we will learn unit number 7 of subject RME. The title of the chapter is Radar Fundamentals. So first of all, we must understand what is meant by radar. So today we are going to see the basic principle of the radar range equation, radar signal characteristics, and display methods of the radar. So first of all, introduction to the radar. So the word radar is a short form for radio detection and ranging. It is basically means of gathering information about distinct objects or targets by sending electromagnetic waves to them and therefore analyzing reflected wave or echo signals. The term radar was officially coined as an acronym by US Navy Lieutenant Commander Samuel M. Tunker and F.R. Firth in November 1940. The acronym was by agreement adopted in 1943 by the Allied powers of World War II and thereafter received general international acceptance. The re-radiated energy and being received back at the radar station gives information about the location of the target. The location of the target includes radar range, angle, and velocity parameters. The range is the distance of the target from radar station. The angle could be azimuth or elevation angle for static target and velocity for the moving target. Velocity for the moving target. So now we'll see the basic advantages of the radar. So very first and important advantage is radar can see through the darkness, haze, fog, rain, snow, clouds, mist, etc. So it can penetrate through any kind of medium. The radar signal can penetrate insulators. It can give the exact position of an object. Radar can determine the velocity of the target. It can measure the distance of an object. It can tell the difference between stationary and moving targets. Radar signals do not require a medium of transportation. Radar signal can target several objects simultaneously. It allows for 3D imaging based on the various angles of a return. It is wireless and does not rely on wire connectivity. And very important advantage, it is cheaper as compared to the other systems. The high operating frequency allows for storage of large amounts of data. It covers a wide geographical area. So these are some limitations of the radar. Radar takes more time to lock on an object. Radar has a wider beam range, over 50 feet diameter. It has a shorter range, means we can operate it only up to 200 feet. It cannot track if an object is decelerating at more the 1 meter 1 mph per second. Large objects that are close to the transmitter can saturate the receiver. Radar can be interfered by several objects and mediums in the air. It cannot distinguish or resolve multiple targets. It cannot differentiate the color of the object. So these are the applications where we can use the radar. So we can use the radar in military application. We can use the radar in air traffic control system. We can use it in the remote sensing. We can use it for ground traffic control. And radar can be used in the space. Now we'll see the basic working principle of the radar. So this is the block diagram for understanding the basic principle of the radar, which consists of transmitter, receiver, duplexer and antenna. The simple radar system consists of transmitting antenna and receiving antenna connected to the transmitter and receiver respectively, such as a radar system is called bistatic radar. The transmitted radiates or transmits electromagnetic radiations generated by a magnetron oscillator. A portion of this transmitted signal is intercepted by target and is re-radiated in all directions. The receiver antenna collects a return echo signal and delivers it to the receiver, where it is processed to detect the presence of the target and to extract its relative velocity with respect to radar station. If the target is moving, so this is the basic principle. Later on, some modifications are done in the radar, in which the function of the duplexer is added So in the modified radar, we are using the duplexer. The function of the duplexer is to isolate the transmitter and receiver during transmission and receptions, to protect the receiver from high power transmitter, to help us to use it as a single for a transmitter antenna or as a receiver antenna. Such a radar where single antenna is used for both transmitting and receiving is called monostatic antenna. Monostatic radar, which is the most useful form of the radar. So now we will see the radar range equation for free space. The derivation of radar range equation is given here. The standard form of radar range equation is also called as a simple form of radar range equation. Free space basically indicates that there are no obstacles between radar antenna and target. Also, free space medium is transparent, that is, no absorptions of electromagnetic waves, and homogeneous with respect to the refractive index at the radar frequency. If the power of the radar transmitted is denoted by Pt, and if an isotropic antenna which radiates power uniformly in all directions is used, then power density at a distance capital R from the radar is equal to the transmitted power divided by the surface of the area of a sphere of radius r. The power density at a distance r from an isotropic source is mathematically represented as in this equation, that is PDI, that is power density at a distance, is equal to Pt divided by 4 pi by r square, where Pt is the amount of power transmitted by the transmitter. Radar usually employ directive antenna to direct the transmitted power Pt into some particular direction. The gain G of an antenna is a measure of the increased power radiated in direction of target as compared with the power that would have been radiated from an isotropic antenna. The power density at a distance r from directive antenna of a power gain G, it can be given as in equation number 2. In general, radars use directional antennas, therefore the power density pad due to directional antenna will be, so we need to add here the gain G. Then the target radiates the power in different directions from the received input power. The amount of power which is reflected back towards the radar depends on its cross section. So the total power intercepted by a target having an area, that is sigma, can be given as shown in equation number 3. So substitute equation number 2 in equation number 3. So we'll have this equation number 4. The amount of power PR received by the radar depends on the effective aperture AE of the receiving antenna. So the PR is equal to PDE into AE. It will be equation number 5. So put this equation number 5. Put equation number 4, this PDE equation, in equation number 5. So we'll get this equation for PR, and after simplifying this equation we'll get the equation for the R, and which is nothing but the equation for radar range. Now the standard form of radar equation can be written as the echo signal is having the power less than the power of minimum detectable signal, then radar cannot detect the target since it is beyond the maximum limit of the radar's range. Therefore, we can say that the range of the target is said to be maximum range when the received echo signal is having the power equal to that of minimum detectable signal. We will get the following equation by substituting R is equal to R max and PR is equal to S minimum in equation number 7, in equation number 6, and finally we will get, after simplification, the equation number 7, which is nothing but the radar range equation, the standard form of radar range equation. So here in this equation, this G is equal to transmitter gain. Its equation can be written as G is equal to 4 pi AE divided by lambda square. Lambda is nothing but the wavelength of the radiated energy, and AC is nothing but, or AE is nothing but the area of the receiving antenna since standard radars generally use the same antenna for both transmitter and receiver. So this RMAX is the standard form of the equation for radar range.